The day the sun attacked, how modern tech would survive the 1859 solar storm. Picture this. It's September 1st, 1859. Richard Carrington, an amateur astronomer in the quiet English town of Redhill, is doing what he does every clear morning, sketching sunspots through his telescope. The sun's surface churns with dark blemishes. But today, something is different. Suddenly, without warning, a blinding flash of white light erupts from the solar disk. It's so brilliant that Carrington can see it even through his protective filters, searing itself into his retinas like a cosmic camera flash. He has no idea he's just witnessed the opening shot of humanity's first space war. Within 17 hours, the entire planet Earth falls under siege. Telegraph lines across the globe begin sparking and catching fire. Operators receive electric shocks so severe they're thrown from their chairs. Papers ignite spontaneously. In the strangest twist of all, some telegraph operators discover they can send messages after completely disconnecting their power sources. The electromagnetic storm itself is powering their equipment, turning the atmosphere into a giant battery. But the real spectacle is in the sky. Aurora borealis, the northern lights, appear as far south as Cuba and Hawaii, places where such phenomena had never been recorded. The lights are so brilliant that gold miners in the Rocky Mountains wake up at 1 in the morning, cook breakfast, and start their workday, convinced the sun has risen on an unusually cloudy morning. In Boston, people read newspapers by the ghostly red glow. Children in Ohio cower in terror, believing the world is ending in fire. What Carrington witnessed was the most powerful geomagnetic storm in recorded history. A cosmic hurricane that would forever change our understanding of the sun's power to reach across 93 million miles of space and touch our world. But here's what should terrify you. If the same event happened today, you wouldn't be reading this story on your phone, computer, or tablet, because none of them would work. The Carrington event of 1859 struck a world with exactly one electronic technology, the telegraph. Today, we've built a civilization that can't survive without electricity for more than a few hours. We have 8,000 active satellites orbiting overhead, fiber optic cables crisscrossing the ocean floors, power grids spanning continents, and quantum computers operating at temperatures colder than deep space. Our entire technological civilization exists in a delicate electromagnetic balance that a solar storm could shatter in minutes. But here's the twist that even the experts are just beginning to understand. We might actually be ready for it. The story begins in the ice. Deep in Antarctic ice cores, scientists have discovered something that should make everyone lose sleep. Frozen in layers of ancient ice are traces of carbon-14, created when cosmic rays slam into our atmosphere. The spikes in these isotopes tell a story of solar violence that makes the Carrington event look like a gentle summer breeze. Around 774 AD, an event occurred that produced the largest and fastest rise in carbon-14 ever recorded. Scientists call it the Miyake event, and it was 60% more powerful than the storm that crippled the telegraph networks of 1859. These cosmic time bombs don't just happen once and disappear. Ice core analysis reveals that solar storms of Carrington-level intensity occur roughly every 500 years. We're 165 years past the last one. The clock is ticking, and the sun is approaching solar maximum, the peak of its 11-year activity cycle right now. But here's where the story takes an unexpected turn. While scientists and politicians debate worst-case scenarios, engineers around the world have been quietly building humanity's first comprehensive defense against solar storms. And some of their solutions are so clever, so unexpected, that they're already changing how we think about the relationship between Earth and space. Let me tell you about the day SpaceX lost $50 million to prove a point about space weather. February 4, 2022. Elon Musk's company launches 49 Starlink satellites into orbit, part of the ambitious plan to provide global internet coverage from space. The satellites deploy perfectly, their solar panels unfurl, and their systems come online. But within days, 40 of them begin tumbling helplessly toward Earth's atmosphere, where they burn up like expensive shooting stars. The culprit? A geomagnetic storm so minor that most people on Earth never noticed it happened. The storm heated up the upper atmosphere, increasing atmospheric drag on the satellites and pulling them to their doom. If a minor solar burp could destroy $50 million worth of cutting-edge technology, what would a Carrington-level event do to the 8,000 satellites currently orbiting our planet? The answer is both worse and better than you might expect. NASA scientists have discovered that solar storms affect satellites differently, depending on their altitude and protection. The most vulnerable are those in low Earth orbit, like the doomed Starlink satellites. But humanity's most critical space assets, the satellites that control GPS, weather forecasting, and military communications, orbit much higher, around 22,300 miles above Earth. At that altitude, they're equipped with what engineers poetically call sunglasses, gradually darkening filters that protect their sensitive electronics from solar radiation. More importantly, satellite operators have learned to play cosmic hide-and-seek with solar storms. When space weather forecasters detect an incoming coronal mass ejection, satellite controllers can shut down non-essential systems, orient their spacecraft to minimize exposure, and wait for the storm to pass. It's like battening down the hatches before a hurricane. Except the hurricane is traveling at 1,000,000 miles per hour and made of electrified plasma. But satellites are just the beginning of the story. The real plot twist involves something most people never think about: the internet cables lying on the ocean floor. Imagine trying to explain the internet to someone from 1859. You'd have to tell them that humans have laid thousands of miles of cables across the deepest trenches of the ocean, cables thinner than your thumb that carry the thoughts, dreams, commerce, and cat videos of billions of people. These submarine cables handle about 99% of intercontinental internet traffic. If they failed during a solar storm, entire continents could be cut off from each other digitally. Most people assume these cables are safe because they use light, not electricity, to carry information. Glass fibers shoot laser beams back and forth across the ocean depths, creating a network that seems immune to electromagnetic interference. But every 30 to 90 miles, these cables need something called repeaters, electronic amplifiers that boost the light signals to prevent them from fading over the enormous distances. And repeaters use electricity. This is where Google enters our story as an unlikely hero of space weather research. Google has invested in 22 submarine cable projects worldwide, representing billions of dollars in infrastructure. When solar physicists started warning about the vulnerability of submarine cables to geomagnetic storms, Google's engineers did something remarkable. They turned their global cable network into a massive scientific experiment. For 5 months, Google scientists monitored voltage fluctuations in their submarine cables, correlating the data with space weather events. They analyzed every geomagnetic storm that occurred during that period, measuring how much extra voltage was induced in cables of different lengths and orientations. Then they did the math to predict what would happen during a Carrington-level event. The results surprised everyone. A solar storm as powerful as the 1859 event would induce about 800 volts of extra current in a typical transoceanic cable. That sounds like a lot until you learn that these cables are designed to handle fluctuations of up to 6,000 volts. The internet backbone, it turns out, might be one of our most solar storm-resistant technologies. But the real story of electromagnetic resilience is being written in the least likely place, underground. The National Institute of Standards and Technology has been working on something called post-quantum cryptography. Encryption methods that even quantum computers can't break. While most people worry about quantum computers making our current security obsolete, these new algorithms are also inherently more resistant to electromagnetic interference. When you rebuild the world's cryptographic infrastructure to survive quantum computing, you accidentally make it more resistant to solar storms too. Meanwhile, at Sandia National Laboratories in New Mexico, engineers have created what might be the fastest reacting protective device in human history. It's a tiny chip made from gallium nitride, the same material used in LED light bulbs, that can detect and respond to electromagnetic pulses in 10 billionths of a second. To put that in perspective, current power grid protection systems react to lightning strikes in about 1/1,000,000th of a second. This new device is 100 times faster. When a massive electromagnetic pulse hits a power line, this device can shunt the excess electricity to ground before it has time to damage transformers or other critical equipment. It's like having a cosmic lightning rod that works at the speed of light. But perhaps the most fascinating defense against solar storms isn't technological at all, it's architectural. At Oak Ridge National Laboratory, researchers discovered that the buildings we construct can either amplify or shield against electromagnetic interference. The secret ingredient, steel rebar in concrete. The steel mesh in reinforced concrete acts like a Faraday cage, protecting the electronics inside from electromagnetic pulses. Large windows, on the other hand, are like open doors for electromagnetic energy, so critical equipment should be kept away from them. This has led to a quiet revolution in data center design. Modern server farms are being built like electromagnetic fortresses, with multiple layers of shielding, underground locations, and backup power systems that can operate for weeks without external electricity. Some companies have converted former missile silos into data centers, taking advantage of the electromagnetic shielding that was originally designed to survive nuclear war. The automotive industry offers another surprising success story. Despite popular myths about electromagnetic pulses disabling cars, most modern vehicles would probably survive a solar storm intact. Car electronic circuits are too short to pick up much electromagnetic energy, and the metal frame provides natural shielding. Even a small percentage of cars breaking down would cause traffic problems, but it wouldn't be the complete transportation collapse that disaster movies love to portray. Commercial aviation, however, presents a more complex picture. Modern airliners are essentially flying computers, with sophisticated electronics controlling everything from navigation to engine management. But the aviation industry learned harsh lessons from lightning strikes decades ago, leading to the development of comprehensive electromagnetic protection standards. Every modern aircraft is designed to handle direct lightning strikes, which produce electromagnetic pulses similar to those from solar storms. The key is making the entire aircraft structure electrically conductive, so electromagnetic energy flows around the outside rather than penetrating to the sensitive electronics inside. It's the same principle as a Faraday cage, scaled up to airplane size. Military aircraft go even further. Strategic bombers like the B-52 have lined curtains that pilots can pull across their cockpit windows during electromagnetic attacks. Special grounding systems throughout the aircraft direct electrical surges away from critical equipment. These planes were designed to survive nuclear war. And a solar storm, however powerful, is less intense than a nuclear electromagnetic pulse. The real question isn't whether individual technologies can survive a solar storm, but whether the complex systems that connect them will hold together under stress. This is where the story becomes a race against time. Power grids are simultaneously the most vulnerable and most critical part of our infrastructure. A grid failure can cascade through every other system: communications, transportation, water treatment, food distribution, medical equipment. The good news is that utilities have been quietly hardening their systems for decades. The Federal Energy Regulatory Commission has identified about 30 high-voltage transformers as critical to the entire North American power grid. Losing just 9 of them in the right combination could trigger a coast-to-coast blackout. But these transformers are now monitored 24/7, with real-time space weather data feeding into automated protection systems. When space weather forecasters detect an incoming solar storm, power grid operators can take preemptive action. They can reduce power generation, disconnect vulnerable equipment, and reconfigure the grid to minimize the impact of geomagnetic currents. It's like preparing for a hurricane, except the storm is invisible and travels at the speed of light. The key insight is that geomagnetic storms don't just appear without warning. Solar observatories can detect coronal mass ejections when they leave the sun, providing anywhere from 13 hours to 3 days of advance warning before they reach Earth. That's enough time to implement protective measures across multiple industries. The Deep Space Climate Observatory, orbiting at the gravitational balance point between Earth and the Sun, serves as humanity's early warning system. From its position 1.5 million kilometers away, it can detect incoming solar storms and beam warnings back to Earth at the speed of light. A new satellite called SWF-OL1, launching in 2025, will provide even more detailed advanced intelligence about approaching space weather. But perhaps the most remarkable aspect of our solar storm defenses is how they are being developed through international cooperation. Space weather is a global problem that requires global solutions. European power grids, with their shorter transmission lines and distributed architecture, are naturally more resistant to geomagnetic storms than North American systems. Asian internet infrastructure centered around Singapore's strategic location maintains better connectivity during space weather events than networks dependent on long trans-Pacific cables. Scientists worldwide are sharing data, coordinating observations, and developing common standards for space weather resilience. It's one of the few areas where geopolitical competition takes a back seat to human survival. The insurance industry is also quietly preparing for the inevitable. After initially ignoring space weather risks, major insurers are now developing coverage for solar storm damage. They learned expensive lessons from pandemic preparedness, or rather, the lack thereof. When COVID-19 struck, almost no businesses had pandemic insurance because almost no insurance companies offered it. The industry is determined not to repeat that mistake with space weather. Economic modeling suggests that protecting critical infrastructure against solar storms would cost between $10 and $30 billion globally. That sounds expensive until you consider that a Carrington-level event today could cause $2 trillion in damage in the United States alone. The math is compelling. Spend a little now or lose everything later. But beyond the economics and engineering, there's a philosophical dimension to humanity's solar storm preparations. We're learning to think of Earth not as an isolated planet, but as part of a dynamic space environment. The sun isn't just a benign source of light and heat, it's an active, sometimes violent star that can reach across interplanetary space to touch our world. This shift in perspective is driving innovations that extend far beyond space weather protection. Quantum computers being shielded from magnetic interference will enable new discoveries in physics and materials science. Power grids designed to survive solar storms are also more resilient against cyber attacks and natural disasters. Communication networks hardened against electromagnetic pulses can better serve remote areas and disaster zones. In a strange way, preparing for solar storms is making human civilization more robust in every direction. The story of humanity's relationship with space weather is still being written. On July 23, 2012, the Sun unleashed a solar storm as powerful as the Carrington event, but Earth was simply in the wrong place at the wrong time. Or rather, the right place at the right time. The storm missed our planet by about 9 days of orbital motion. If it had hit, the world would be very different today. We got lucky once. We probably won't get lucky again. But here's the remarkable thing. For the first time in human history, we don't have to rely on luck. We're building a technological civilization that can survive the worst the sun can throw at us. From gallium nitride switches that react in billionths of a second, to submarine internet cables designed to handle massive voltage spikes, to quantum computers shielded by active magnetic cancellation. We're creating defenses that would have seemed like magic to Richard Carrington. The next time the sun attacks, we'll be ready. The question isn't whether another Carrington event will happen. It's whether we'll finish building our defenses before it arrives. Current estimates suggest we have a 1.6 to 12% chance of experiencing a Carrington-level solar storm within the next decade. Those might seem like small odds, but they're large enough to justify the massive engineering effort now underway to protect our technological civilization. When that next solar storm arrives, and it will test everything we've learned about living as a technological species in the cosmic environment. The aurora will dance in skies where they've never been seen before. Power grids will strain under electromagnetic loads they were designed to handle. Satellites will hunker down behind their electronic shields. Internet traffic will reroute through protected cables, and billions of people will continue with their daily lives, most of them unaware that they've just survived humanity's greatest test of technological resilience. The sun giveth, and the sun taketh away. But this time, we're ready to fight back. Richard Carrington's white flash changed the world once. The next one will prove that we learned the lesson.